The National Electrical Code, or NEC, does not permit splicing an oversized conductor installed to mitigate voltage drop to a smaller conductor that properly fits a circuit breaker. The primary reason for this prohibition lies in the fundamental principles of overcurrent protection. A circuit breaker is designed to protect conductors from overcurrent conditions such as overloads and short circuits. Its trip rating is carefully selected based on the ampacity of the conductor it is intended to protect. The ampacity of a conductor is the maximum current, in amps, that it can carry continuously under specific conditions of use without exceeding its temperature rating. When a conductor is oversized to address voltage drop, its ampacity is higher than that required for the load it serves. This is acceptable because the increased conductor size does not compromise the overcurrent protection. The circuit breaker still protects the conductor according to its designed ampacity. However, when an oversized conductor is spliced to a smaller conductor, the situation changes drastically. The smaller conductor now becomes the weakest link in the circuit. If an overcurrent condition occurs, the smaller conductor will be subjected to current exceeding its ampacity before the circuit breaker trips. This can lead to overheating, insulation damage, and potentially a fire hazard. To illustrate this further, consider an example. Suppose the circuit requires a 12 American wire gauge, or AUG, copper conductor with an ampacity of 20 amps. Due to voltage drop considerations, a 10 AWG copper conductor with an ampacity of 30 amps is installed for the majority of the circuit run. However, at the circuit breaker, this 10 AWG conductor is spliced to a short length of 12 AWG conductor to facilitate connection to the breaker terminal. In this scenario, the 20 amp circuit breaker will only trip when the current exceeds 20 amps. If a fault current of, say, 25 amps flows through the circuit, the 12 AWG conductor will be subjected to an overcurrent condition exceeding its 20 amp ampacity. This could cause the 12 AWG conductor to overheat and potentially fail before the circuit breaker trips. The NEC addresses conductor ampacity and overcurrent protection in several sections, including Article 240, which covers overcurrent protection, and Article 310, which deals with conductors for general wiring. These articles emphasize the importance of matching the overcurrent protection device to the ampacity of the conductors being protected. The code mandates that overcurrent protection devices, such as circuit breakers and fuses, must be selected and installed to protect conductors against overcurrent conditions. This protection must be based on the conductor's ampacity, taking into account factors such as conductor material, insulation type, ambient temperature, and the number of conductors bundled together. Moreover, the NEC provides specific requirements for conductor splices in section 110.14b. This section states that splices must be made with splicing devices suitable for the use. Splices must also be insulated to a degree equivalent to that of the conductors. While this section does not explicitly prohibit splicing an oversized conductor to a smaller conductor, it implicitly discourages the practice by emphasizing the importance of maintaining the integrity and safety of the wiring system. The use of an undersized conductor at a splice point creates a point of vulnerability in the circuit, negating the benefits of using an oversized conductor for the majority of the run. The correct approach to address voltage drop and ensure proper overcurrent protection is to use appropriately sized conductors throughout the entire circuit. If an oversized conductor is needed to mitigate voltage drop, it should be run continuously from the source to the load, without any splices to smaller conductors. The circuit breaker must be sized to protect the smallest conductor in the circuit. If the oversized conductor cannot directly terminate at the circuit breaker, a listed and labeled terminal adapter or lug should be used to facilitate the connection. These adapters are designed to accommodate conductors of different sizes and ensure a secure and reliable connection. Another method to consider is using a circuit breaker with terminals rated for the larger conductor size. Some circuit breakers are designed to accept a wide range of conductor sizes, eliminating the need for splicing or adapters. It is crucial to consult the manufacturer's specifications to determine the acceptable conductor size range for the circuit breaker terminals. Furthermore, careful consideration should be given to the voltage drop calculation itself. Accurate voltage drop calculations are essential for determining the appropriate conductor size for a circuit. The NEC provides guidelines for voltage drop calculations in Informative Annex D. These calculations should take into account the length of the circuit, the load current, the conductor material, and the conductor temperature. Using online voltage drop calculators or consulting with a qualified electrical engineer can help ensure that the correct conductor size is selected. In addition to conductor sizing, other factors can influence voltage drop, such as the power factor of the load and the presence of harmonic currents. Improving the power factor of the load and mitigating harmonic currents can reduce voltage drop and allow for the use of smaller conductors. Power factor correction can be achieved by installing capacitors at the load or at the service entrance. Harmonic mitigation can be accomplished by using harmonic filters or reactors. When dealing with long circuit runs or high current loads, it may be necessary to consider using parallel conductors. Parallel conductors are two or more conductors connected in parallel to increase the overall ampacity of the circuit. The NEC permits the use of parallel conductors under certain conditions, as specified in section 310.10h. When parallel conductors are used, they must be of the same material, have the same circular millet area, have the same insulation type, and be terminated in the same manner. The overcurrent protection device must be sized to protect the parallel conductors according to their combined ampacity. It's also important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Improper wiring practices can create safety hazards and violate electrical codes. In summary, splicing an oversized conductor to a smaller conductor at a circuit breaker is not permitted by the NEC because it compromises overcurrent protection and creates a potential fire hazard. The correct approach is to use appropriately sized conductors throughout the entire circuit, or to use listed and labeled terminal adapters or lugs to facilitate the connection of the oversized conductor to the circuit breaker. Always consult the NEC and local electrical codes and engage qualified electricians to ensure safe and compliant electrical installations. Proper conductor sizing and overcurrent protection are essential for maintaining the safety and reliability of electrical systems. Ignoring these principles can lead to dangerous situations and costly repairs. Therefore, it's crucial to prioritize safety and adhere to established electrical codes and standards.